Today we're going to talk about Lab 1, a lab in which we're going to evaluate the performance of some key value pair data structures. Yeah. So what's a key value pair? A key value pair is a data structure that essentially has bits of data, but there's an important value called the key that we use to kind of represent that data, and we would do lookup and therefore insertion and deletion based on that key. And the reason why this matters in the broader context, like it's not just some goofy arbitrary data structure or model that I'm making up. There's a lot of real world systems that work this way. It's sort of the foundation of databases. A key pattern in databases is that every item in a table has a key. I didn't mean to say key twice. It was just a happy accident. It's like that is the essential aspect of what makes databases good at looking stuff up for the most part, is there's a value that's special, generally called the ID, that uniquely identifies each row, and we make the database so that it's really easy to look stuff up based on its ID. And that's why, I mean, you've seen this even trickle up to your real world. I thought this was dumb. Usually the ID in the database isn't necessarily human meaningful, but our current colleague system that shows you your colleague ID, which is an arbitrary number that really just exists for the system to maintain consistency, but they make me put it on certain forms. I guess to make sure you're the Robert Smith and not some other Robert Smith. But anyway, IDs matter, and so key value data structures matter. We've already learned two broad ways of doing this. Hash tables last semester, which C# calls a dictionary. And so we're going to use the built-in dictionary to do key value operations. We know that key value operations in a hash table should be crazy fast because the three main operations, add, remove, and lookup, are what time complexity? Constant? Yeah, O of 1. So that's really good. So that should be our leader. In this current module, we've been looking at trees, specifically binary search trees that have the same pattern of key value pairs. They are not quite as fast, but if they're balanced, then they'll have what time complexity on the three main operations? They'll have log n, which is good. So instead of us coding up the balanced binary search trees, we're going to test them with code using benchmarking software. Can y'all see the screen okay? All right. For a long time, I did benchmarking the low-key way. That is the informal, unscientific way, which was you just basically start a stopwatch in your code, remember the time, execute the code, click the stopwatch again, and then subtract the two, and you'll get how long did this thing take. Does that make sense? And that's an okay way. I mean, even when we did it, I would say you got to run it like 100 times or 1,000 times, and then take the average, so that if there was some variation in that, you could average it out. The thing is, even doing that is not enough to be truly accurate and like scientifically rigorous, because your computer is doing all kinds of other things at the same time that it's running any piece of software. So how do you know, like if you're playing, what is it y'all play these days? Fortnite? Call of Duty? Is that still a thing? I'm sorry. That Silver Surfer game that Abby was so good at? What was it? Not Silver Surfer. Subway Surfer. If you're running that and then running these tests in the background, then certainly it would make sense that these are going to be slower, right? So how do you know you're not measuring all the other programs that are running at the same time? And there's a bunch of other ways that you could be not capturing a good measure of how long is this taking. So the right way to do benchmarking is really complicated, but fortunately, there is benchmark.net. There's many like open source packages that do benchmarking correctly and take care of all those dirty details that we really don't want to do. So we're going to use benchmark.net, which seemed to be the most popular one for .NET stuff. And I'd like to just give you a super brief introduction to benchmark.net. It's super easy. On the whole, it makes it so that you can very quickly just say, you can annotate a method and say, I want to measure how long it takes to run this method. More than that, I'm going to vary some variable over a particular set of values. So I'm going to check n equals 100, and n equals 1,000, and n equals 10,000. And it's a really easy way of doing that. And it handles all the complexity of how many times it needs to run it to get a consistent average. It'll do that. So like a lot of smarts are built into this that I don't even know what they all are, but I know that this is going to produce a more reliable output. Okay. So I'm going to, within this, would normally code like this, but I am today. I'm going to create a public class string benchmark. So this is a class that's going to benchmark some stuff with strings. And what I'd like to do is analyze the performance, benchmark the performance of two different ways of building a string by appending more characters to a string. So the first method I'm going to write here is a public string, simple string builder. And in this method, I'm going to do this the naive way. I'm going to have a string result that's equal to nothing. And then I'm going to return the result. And then the work that I'm going to do is I'm going to say for int I equals 0, I is less than, let's say 100, I plus plus. And I would like to take my string that's result and concatenate I, which it's going to call to string implicitly. I don't think I actually have to do that. But so this is, I'm not doing integer addition. I'm going to put 0, 1, 2, 3, 4, all in one long string. I don't know if you remember this, but I believe that strings are immutable. Strings are immutable, which is confusing, right? So what this means is when you assign a new string to an existing string, what really has to happen is we have to make a new string that's a copy of the first one and the second one, but it's at a different memory address each time because once you've created the string, it's immutable. All right, so that's what's happening behind the scenes. So actually, though, this looks simple, but it's actually doing a lot of work. You with me? Because it's not actually changing the thing in place. If you wanted to change it in place, then let's do this a little bit smarter. So we'll have a different method, which is a public string, better string builder. I'm kind of going into this knowing which one's better. I guess in real life we would say, you know, they just have two different names, and the benchmark would reveal which one's better. What's it? Okay. So here's what we're going to do. Instead of just creating a string, I'm going to use the string builder class, which is built into .NET. Result is equal to a new string builder. So this is the class that's made for essentially creating a mutable string. I'm going to copy paste all this because I believe this is almost the same. Sorry. We can't plus equals, but we can dot append. And then down here, I do have to take the string builder and convert it back to a string, which is an immutable string. So I know this looks really similar. Does it make sense what's happening here? I'm doing all this not to demonstrate key value pairs or trees or anything, but just to build up our benchmarks. Okay, so I've already included the benchmark.net into this project. Um, which I should show you how to do that at some point. The .NET has a mechanism for adding packages. Most programming languages have a mechanism for easily adding software that somebody else has written to their code. .NET's is called NuGet, N-U-G-E-T. Other languages and frameworks have other mechanisms for doing that. A lot of web stuff uses NPM, the Node Package Manager. If you're in a JavaScript, TypeScript, really almost anything webby, you would use NPM. If you use the Go language, they have GoGet. Basically, all languages have that now. Okay. Sorry, I skipped that step. It would have been better if I'd showed you that. Okay, so now you'll notice I'm not even calling this code. So let me see if I can't run this. All right, I've got to do a couple of things first. For each of the methods that I want to benchmark, I have to put this benchmark annotation in square brackets above it. So for these two methods, I want to mark them both as benchmark methods. I believe that I also need to say on the class here, this whole class that has the benchmarks in it, I want to say that this is a short run job. That'll kind of control how many times, like does this happen 100 times, does this happen 1,000 times? I would rather this run shorter. Okay. And then I would like to .NET build. Let's see what happens here. Let's see. What am I doing wrong? Is it because I'm in the outer folder? Okay. Oops. I want to run this. I do want to run it in release mode. Actually, that's not enough because it can't find a project to run. Ensure a project exists in that, or pass the path to the project using it. What I did before. Okay. So it ran and it didn't do anything. That is, we didn't see our output. Um, because there's a line that I skipped, which is I have to, in my main method, tell it to run the benchmarks. So it looks like to do that, I just say benchmark. It's benchmark runner dot run, and you can put in here the name of the class that you want to run your benchmarks on, which ours would be called string benchmark as the generic parameter. I'm pretty sure I can just do it this way. And it might be that I want to get some result back. I can't. Yeah, I'm not using it. Dot run returns reports. It's also going to print it out on the command line, which is how I would use it. Okay, so these are like data, the benchmark data. So this is the key thing that I was forgetting, which is telling our code which benchmark classes to run. That is, which classes that have methods with the benchmark annotation. Okay, so let me try this again. And now you'll see it's doing this test to figure out how much work it has to do. As you see, it's taking a lot of measurements in nanoseconds per op. And then it does the work, finally, after a bunch of warm-up. So notice here, the simple string builder took 1,418.7 nanoseconds on average, and the better string builder was 360.7. This is better. Yeah. It also gives you the standard error and the standard deviation if you get into those kind of statistical metrics so that you can capture how much variability there was. This is the definition for error. So that means there's a 99.9% confidence interval. On either side of 86 nanoseconds, half of 86, 43. I think that means there's a 99% confidence that this number is correct to within 43 nanoseconds. That's the way I read that. You with me? And a lot of what it did was to make sure that we had a low error. Here's what it does by default. Okay. Questions on this? At this point, there's a couple more things I do want to show you. So this is doing the hard work of correctly measuring the timing of these benchmark methods. But that's not all. There's more. You can, if you know it, tell this benchmark that the called baseline equals true. So I'm going to mark the case that I'm saying my simple string builder is kind of my baseline method. And if it knows that this is the baseline, then any other methods that can do the same thing, which in this case would be the better string builder, I only have one other one, it can compute percentages and see how much better it is. Another thing that you can do is you can measure how much memory is used in addition to just measuring time, which that's something I never would have done in this class manually. So with this one attribute here, memory diagnoser, it will also capture how much RAM was used to do this. Which, remember, that's the two main ways that we measure the complexity of an algorithm is what's its runtime complexity and what's its space complexity. Right? Time and space are the two things we measure. In this case, we're not measuring the big O complexity. We're measuring actual, how much did it use on my computer. To get the best results, you should, and even believable results, accurate results, you should use the release mode. There's debug mode. That's one way to compile, and release is a different set of compiler settings. If you know you're going to have to debug your stuff, then the compiler leaves in a lot of extra junk so that it can debug and you can get that step by step. Does it make sense that it would take some effort to be able to debug? If you know you want to make this thing as fast as possible, you put it in release mode and the compiler you will then turn on all these optimization settings and it'll strip out all that debugging info that's not needed, and you'll get the best possible performance for a particular set of code. I guess the trade-off is it would take more time. It might take more time compiling it, but that's worthwhile if you want the best performance, right? Which is what we're doing to test. So I'm going to rerun this and see how this changes when I rerun it, having turned on the memory diagnoser and the baseline. NS is nanosecond and US is microsecond. If you see that come up, you may be on different scales. I'm just doing 100 things, which is really small. Like nanoseconds are crazy small. I would almost even not fully believe it. There's a limit to how fine of a resolution in time your computer can measure things. So it looks like this time you see the table's a lot bigger, but you can see a ratio. So whatever you set as your baseline is marked as a 1.0. So this says, hey, this took 25% of the time, this number versus this number, so that's pretty useful. And then I believe this Gen 0 and allocated are measures of the amount of RAM that was allocated. This is the garbage collector. Generation 0 collects per 1,000 operations. So you kind of have to get into knowing how the garbage collector works to understand this. And I'm not a garbage collector expert. I believe that that lower is better, is what's happening here. Same for here. Like this makes sense, right? That even though you couldn't see it, this had to allocate 20K of RAM to do it the naive way. Because every time we appended, we actually had to copy into a new place in RAM. Whereas when we use the string builder class, we only had to use 1.25K of memory. So this algorithm is better in both time and space complexity. And I believe, yeah, this allocation ratio is showing you, if this is 1.0, that's like, because that's your baseline, this is just 6% of the memory to do the better way. Does that make sense? So I think it's nice that without you having to do a bunch of the gross work that's easy to do wrong. If you ever read a benchmarking article online, people will always be like, well, you did this wrong. That's not even fair, is my experience. Because there are a lot of ways to do it wrong, and then that completely biases your results. So these are, in my mind, benchmarking experts that actually took the time to do it well, and we get to build on top of them without knowing how many things there are to do wrong. So that's a win. And I think then we can trust these numbers that are coming out. So what we're going to do is evaluate a dictionary versus an unbalanced binary search tree, a plain old binary search tree, versus an AVL tree versus a red-black tree. And see how they do in terms of how fast does it take to insert a set of things, how long does it take, that is, to look up a bunch of things, how long does it take to delete a bunch of things. Yeah? Let me see if I can do this. Try one more thing. I believe that I can come down here and I can say I have a public int in. Okay? This is in. And instead of going to 100, I would like to go to in for both of these. So what I'm saying here is, instead of just hard coding in, do this 100 times, I would like to vary the input size and see how the algorithm scales as n gets bigger. And naively, you might create a for loop where you iterate over the particular values that you want and then repeat this. But they've got a special way of doing this so that it's really easy. And all you have to do here is put a params attribute and then list the parameters that you want. So if I want to check 100 and 1,000, let me do 100, 500, and 1,000. So now I would like essentially to do these benchmarks for these three values of n. You with me? It's going to take longer, but we get all this data such that we could create a chart. Okay. Just want to do that again. This will take longer. And while that's doing that, I would like to come over here and just look up benchmark.net. So we've learned most of this already. Looks like we did params. We've marked something as benchmark. Another thing that's often done in benchmarks is you've got to do some setup at the beginning to like, hey, let's create, in this case, we're going to need to create 1,000 random key value pairs. We want it to be the same in key value pairs so that we can insert them all into the data structures. You with me? And we don't really want to measure how long it takes to generate all those key value pairs randomly or to read them in from a file or whatever. That getting them in isn't the thing we want to test. Does that make sense? The system has to have some starting state before we do the thing we want to measure. So the global setup basically means run this once at the beginning. And then once this has been run once at the beginning, then do your benchmarks. But you can trust that when you do your benchmarks, this code has been run. Let's see. All right, let's see what we got. Now I'm exceeding my width. Okay, so now that there are different variables, you see this column n. So I've evaluated the simple and the better for 3 different values of n. Not surprisingly, my mean time went up. I mean, I did 5 times as much work here, and then I doubled it again here. I still get all these same things. I guess depending on how many times the garbage collector has to run, there's this Gen 0 and Gen 1. But you can see here what a little bit of how it scales, right? So, I mean, you kind of need to put this on a chart, but how does this 1.4 nanoseconds, no, that would be 1.4 microseconds, compared to 35 microseconds, compared to 132 microseconds? Is that 5 times as much? No, it's worse than that, isn't it? It's a lot worse than that. Whereas this one, I think that is almost scaling linearly, isn't it? Yeah, that's very linear. The string builder is. So from this, I'm beginning to see it looks like the simple string builder way has something that's above linear. Maybe it's quadratic as it scales up. That's quadratic looking, right? Okay. Thoughts, questions? This is cool, right? I'm always torn on this as to how much to make y'all do versus how much to just give you. On the whole, this project isn't about coding. It's about evaluating the performance of the data structures that we've learned. So let me show you in here. This DSA is a folder where I've pulled out some data structures and algorithms from a open source collection of data structures and algorithms implemented in C#. I don't know if I can show you where it came from if you're interested. It was an open source repo on GitHub where somebody implemented these. C# has a built-in dictionary, but I don't believe it doesn't have a built-in tree structure. So this is somebody's implementation. So if we look at this, maybe let's start with the simplest. This is the one we know. This is a binary search tree map. If they do a key value mapping, this creator, this code author calls it a map because you're mapping from a key to a value. Whereas he also has, he or she has an AVL tree, which just would be like a tree of keys, which is the way I always drew it on the board, but it's much more useful if it has a key and a value. You with me? I think it's also cool to like look at what this author wrote. This is somebody who knows C# pretty well, and they wrote, I think, a pretty nice, there's 400 lines of code for this binary search tree map. And what's cool about it to me, let me see if I can't, in here, no, here. These are the methods that are built in. You can see this. Let's find the root. Yeah. So the root is a property. This is all built on the binary search tree map node that is generic in both the key and the value. So T key is the type of the key, and T value is the type of the value. So this is full featured, unlike ours where we made it only support integer keys. This would work for any key that's hashable. I'm sure that's what it is. If we come in here, we could define, we could look up where this is defined. So actually it would be, I guess it doesn't. So here's the, this is the tree map node. So what does a node have? It has a left and a right. It has a key and a value. It has a constructor. You can create a tree map node, and it has this invalidate, which apparently just turns both left and right to be null. So that means there's not a parent in here, is there? Nope, they're not storing the parent. Bold, very bold. It may be the case that in an AVL tree, this is the node for an AVL tree, left, right, key, value. The AVL tree has a height. Remember, that would make sense, right? That every node has a height, and then we can check that if we need to rebalance it. Oh, they did use object-oriented inheritance nicely here. So this AVL tree map node is a binary search tree map node. And so it inherits from that. And what does that mean? That means we get this constructor, and their invalidate just calls the other invalidate. I don't see why didn't they just inherit it? I don't know. Okay. So we're going to get to use somebody else's API, but their API is like pretty straightforward, and you're going to get autocomplete on this. So if you wanted to, say, add a bunch of elements to their binary search tree map, how would you do that? Well, let's see what methods there are. There's an add. That looks very promising. I would suggest you try add. Now, we can see the code and see what it does, which this is equivalent to the code that we wrote. They may be using some better techniques and some more advanced stuff, but you add, you take in a key and a value, check if the root is null, because if the root's null, right, then you've created the new root. This is familiar. Increment, count, and return. That's almost exactly what we wrote. Good job, us. Otherwise, now look, you see this while loop? They did it the iterative way instead of the recursive way. To each his own, I suppose. So you've got to have this while loop to find the right spot to go to. We cannot put duplicate keys in here. That is our requirement as this kind of key value map. Every key must be unique. Yeah, there's where they actually added increment the count. Here's how you remove it, dealing with all that grossness. Here's find and remove the minimum. Wow, that's a method. That is a method. Contains key. For what it's worth, this comparer, it's possible to define your own comparison function as to how you compare two keys. Like if you had two people objects, how do you compare two people? By default, there wouldn't be a way. You can't just like an integer say this thing is less than this thing. But if your class, even your predefined class, your custom class defines how to compare two people. Maybe we compare them by age. Maybe we compare them by their ID in the system. Whatever exists in your system, whatever business logic, you with me? You can implement that, and if you put that in the comparer, then this system can still work, and you can do all kinds of ordered operations if you have a definition of what it means to compare. And sometimes that compare is like decoupled and defined separately. Okay. On the whole, this is not that different than what we did. I mean, actually, we did a bunch more methods that they didn't do. Your work, like all that range search and next and previous, is more complicated than what they did. Okay. So let me, I think I'm just going to give you this, and maybe it's implemented correctly. I don't know. You deal with this. Okay. Oh, here's another cool thing. You can put this annotation here, Markdown exporter, ASCII doc explorer, HTML exporter, CSV exporter. I think this is all of the exporters that they have. And in addition to printing the output to the command line, it'll create a Markdown document and an ASCII document and an HTML document and a CSV document, a file that has the output data. I think it puts it under like the bin folder and release. I don't think I've run these yet, so it wouldn't be there. We can test this and see. And you can choose any or all of these that you want. I was just kind of just create everything and then you can decide what you want. Sometimes it's a pain to copy paste stuff off the command line. So for what that's worth. So there's four main operations that I want our code to test. Four main operations. Insert, remove, lookup, and height. Height isn't an operation, I guess, as much as it's a property of the data structure. Are we good? Everybody feeling okay? So this is a class that's going to measure the insertion of the key value benchmarks, the key value maps, the key value pairs. So in this class, so I made this class just to encapsulate doing this benchmark. I don't know if I would make all classes like this. For example, this is a field and not a property, is public. Usually fields are private and properties are public. So this is going to store, I just have key value pairs that are int to int. I think to keep this simple, like you could make this so much more complicated, but I just made all of the tests be integer to integer. So we're not changing the data type, we're looking at other variables. Meaning, for example, in. What are the different sizes of input? In this case, I'm testing 100, 1,000, 10,000, and 100,000. These are all smaller than I want you to test with on the whole because I want you all to go big and actually make it work for some time and get a feel for how does this work when things get big. Another variable that I want you to test is the ordering of the data. Okay? We know that a binary search tree will operate differently if you insert 100 items in order or if you insert 100 items randomly. right? What's going to happen if you randomly insert 100 items into a BST? That is, the keys are randomly generated. How tall is that BST going to be? How many levels are there going to be? I don't need an actual number, but maybe the formula for the number or the order of the number. That makes sense? If I gave you 7 numbers, how tall would you expect 7 randomly ordered numbers inserted into a BST? How tall would that tree be? It would be about 3, because it's going to be kind of balanced if they're random. What's that relationship between 7 and 3? Rhymes with algorithm, kind of. Logarithm. There's not a lot of words that rhyme with logarithm. So it's going to be about the log base 2 of 100 is how tall it would be if they're inserted randomly. You with me? How tall is the tree going to be if I put in 100 nodes in order? You picking up what I'm laying down? Monica, do you want to say it? Just say it. Okay, I want you to shout it. It's going to be how much? 100. It's going to be that long, gross linked list tree. So that's why I want to test this thing and say, hey, is this in order or not? And how does it handle it if it's in order? Spoiler alert, BSTs are not going to handle it well if it's in order. AVL and red-black trees and dictionaries will be okay. Okay. So this is my global setup. I need to generate a bunch of key value pairs. And the way that I'm doing it here, which is sort of arbitrary, is for all the numbers between 0 and n, I'm creating a new key value pair that goes from integer to integer, that the key is the current I that I'm on, and the value is 10 times that number. That was just an arbitrary formula. You could change that. I don't know if it would be better if it was random or not. It kind of doesn't matter, I think, what the value is. This way it's kind of clear to see. You're going to have 1 and 10, and 2 and 20, and 3 and 30. Okay. If you're testing this such that they're not in order, then I call a shuffle method on the key value pairs. I've generated them in order, right? They go from 1 to n. So they're going to be in order. If you don't want them in order, then I call shuffle. If you command or control click on that, this is an algorithm that I copy pasted off the internet that is apparently a thread safe and like mathematically proven algorithm. There's a fancy name for it. It's like 2 people's names, I think. This is the way to shuffle a set of things and to reliably get them actually shuffled. Like this is sufficiently shuffled. I feel bad that I didn't write the name of this algorithm. As a thing, have we done extension methods in this class? Did I ever give you that assignment? Okay, this is simple and not that complicated. .NET has a feature where, do you see the parameter for this? It says this iList list. By putting the word this here, then this shuffle method actually becomes a method on all lists in this project. So any iList, anything that implements the interface iList in this project now has a .shuffle, even though Microsoft didn't write a .shuffle. You could just as well have called like my extensions .shuffle and then pass in a list. I think that's all it's really doing behind the scenes. But I think this syntax is nice to kind of give the appearance of shuffle being a method that's on list. All right, so that's that. Okay, so how would we insert values into a dictionary, boom. That's it. Create a dictionary for all the KVPs in the key value pairs. What are key value pairs? It's this public variable right here that we just, in our global setup, created a bunch of key value pairs. So global setup, because I've marked it this way, benchmark.net will make sure that happens once before the whole benchmark is run. I think there's also a setup that happens like before each run. So like different levels of, do you just do this once for the whole like 100 times that you run the benchmark, or do you do it once before every run of the benchmark? Okay. So notice all I'm doing is just inserting a bunch of key value pairs and I'm not really doing anything with it. But this is what I want to measure, is how long does it take a dictionary to do 100, 1,000, 10,000, a million inserts? Yeah? Okay. How do you do this into a BST? Well, we're going to use this binary search tree map that I get from the DSA library, this folder here. I believe at the top you'll see, yeah, I've said using DSA data structures.trees. That's the namespace where all the tree data structures are. And then this is the syntax for doing that with an AVL tree map. AVL tree map looks very similar because it's a subclass of a BST tree map. I guess that would be a BST map. And then there's also a red-black tree. So this code is really boring. Do you see how boring this code is? That's why I don't mind giving it to you. There's a little bit of, you got to structure it this way so that this will make it easier to iterate all these parameters without you having to do anything. But in this case, now I have two variables, int, in, and is in order. This variable has 1, 2, 3, 4 possible values. This variable has 2 possible values. So how many different cases are there? I think it's 4 times 2. You were on the right track. I see what you were doing there. So this does expand. I guess the other thing that I didn't say is we actually have 4 different data structures, kind of. In this, the way I did this insert, I made each benchmark, but each method its own benchmark. I think in one of these other ones, I changed it, and I don't know if this is better or not. I was trying to make it easier. I created an enum called key value map type and put in dictionary, BST, AVL, and red black, which are our 4 data structures. You with me? So that I could make that a variable. So now in this, let me skip setup. In this lookup function, there's only one lookup benchmark, and it iterates over all the key value pairs that exist. And then I've got this big switch statement. And if we're doing a dictionary, we get the value out of the dictionary. If we're doing a BST, we get the value out of the BST. You can rewrite this if you don't like this. But this way, there's just one method, lookup, and it actually then has 4 times however many values of in this case 2, times however many values of is in order. So this would be 2 times 2 times 4, which is 16. But that's how many will have to be output from this. Will be output. Does that make sense? And there was a reason why I switched it. I think remove is done the same way, where I just made one method with a big switch statement so that you can iterate, you can make a parameter, parameterize the type of the data structure. Does that make sense? I kind of already have done it for you here. These are the parameter values of in, which I'm going to tell you in the Google Doc what values of in I want you to test. These are just samples of numbers that are really low so that they would run fast. In order needs to be both true and false. And this I must have that. Okay, here it is. Sorry. Key value map type. I've set a params of these 4 values of the parameters. So I was completely overlooking that. So these 3 are the parameters of the benchmark. So now this would be 2 values times 2 values times 4. Again, that should be, there would be 16 cases that come out of this. There's this global setup in all of these for both remove and lookup. You can't do the remove and the lookup until you have a data structure that has all that's been populated. So in each of these, I think there's a so remove is the one that you're benchmarking, but there'll be another method that's all the inserts. So this is a little bit duplicative, but you've got to insert all the values into the dictionary, the BST, the AVL, the red black, before you start removing them. One thing that you're going to need to do, which I will let you do, is in the main method of this project right here, you need to not run the stream benchmark, but run the benchmark runner for each of the ones you want to run. So var data is equal to benchmark runner dot run, and the type that you put into this generic parameter is really the way you specify which benchmarks you want to run. So if I want to run the insert key value map benchmarks, then it's going to look in this class here for any methods that are marked as benchmark and run them. So let me run that and see if that works. So I'm no longer going to be running these string benchmarks. Okay. And I'm sorry, this feels super long there. Is that what do y'all have to specify the project normally? I thought you usually would find the one project that's there, so I don't know what I've done wrong there. Something in my config, it's not finding the project unless I say -- project and then give the path to the project file. If you can figure out the simpler way of doing that, please let us know on Discord or whatever. So I'm going to let this run. I think all those numbers are really small, but it does have to do what we said, like 8 things for insert, because there's the sorted and unsorted, and there's the 2 values, or was it 4 values? Oh yeah, and this one, the way I've done insert, there's actually 4 different benchmarks. Whereas in the others, I made them be one benchmark that has a bunch of parameters. Okay, I had an idea in the shower this morning, which could be really good or might not be. I'm not completely sold on it, but since we're waiting for code to run, if you had the option of writing your report in a pair-based way, what would be the upside downside of that? Is that helpful to have a partner? Is that just really making it like more work? Because I get collaborating with somebody can make it harder, and you are bound sort of to their grade and their work and group projects. But sometimes so I'm at the most saying teams of 2 to write up the lab report, which I'm expecting this to be a good lab report where you actually analyze the effect of these different variables in the different algorithms. Honest discussion on that. I'm not convinced that doing it in pairs actually helps. And I really only want to I only want to do it if it helps you do a better job or learn more. Any thoughts on that? I would not require pairs. I would be pairs if you want it at the most. And you could choose to work alone. Hmm? Okay. I mean, my gut is you would learn more by doing it by yourself. Um, and I guess on the whole, the coding part is almost done. You just have to run it, and you have to manage what the different parameter values are. If I can try to clean that up. I thought it's got to be close. I've seen it pop through here. While that's going, so are you familiar with the term SmackDown? Like Adrian. All right. So these are really the variables that I want to test. 100, 1,000, 10,000, 100,000, and 1 million are the values of n. That's 5 values. And no, they are logarithmically or exponentially increasing. That is not linear. That is not linear. Um, part of me wants to make it more linear and do more data points so that you could see the pattern, but I really like the logarithmic or exponential increase here. I would like you to measure these 5 things: insertion time, lookup time, removal time, the memory allocation on insert, which means you just turn on that memory diagnoser or whatever it was on insert and copy those over, and you can see how much memory is being allocated. And then lastly, and this one's kind of different, is the height. I think this is insightful for the trees to see how tall are these data structures. You with me? How tall are the data structures? And I think I actually already wrote benchmarks to do that. What you're going to be doing is extracting data, and I think you should organize it into a set of tables. You kind of need more dimensions than 2. So that means it's very difficult to create a 4-dimensional table on a Google Doc, though. So you're going to have to slice that down and squish it into 2 dimensions, as it were. So for example, for insertion times, these are the data structures. And I've actually squished the ordered and randomized into just different rows of the same table. But really, that's kind of a different dimension. And then you would copy over what those values are. Is what I would put this in a. I would put it in a spreadsheet if it were me. I guess it could be tables in a doc. If there are some tests that take unreasonably long to finish or crash on your computer because your computer has run out of memory, then put like a dash dash or an NA or something. And that should happen on BST ordered. That you're just not going to be able, you can't put a million things in a BST ordered. It runs into an issue, I'm pretty sure, a memory issue. It's like a stack depth. Okay. All right, here's my mega results here, just so you can kind of see for the different values. What, 100, 1,000, 10,000, oh, and 100,000? Oh, that's what the values that I had? Oops. That's it, right? So how long did it take to put in the dictionary? 890 versus 1,700 versus 5,300 versus 3,500. This was not in order. So how would you make sense of this? Why is AVL tree so slow? I thought it was good. It's doing a lot of work to stay super clean. Let's note how that scales up. Let's just look at that one question, maybe of BST versus AVL. Can we do that? So going up to, and actually let me just compare it to other falses. So these are still randomized. So BST at 1,000, 27,000 nanoseconds. That would be 27 microseconds. 98 is still a lot, 62 is still a lot. So it's still randomized. The BST is better. It's a lot faster to insert into that. Interestingly, when we go up to 10,000, 650 is still way faster than this 1,500. Notice though, both of these are pretty close to 1,500. Why is that when I have 10,000 things, remember the red-black tree is doing less work, but now it's not, like in this case, it was like 50% faster. And now it's the same. Well, why is that the case, I wonder? You got thoughts, Annika? Mark? Well, from what you know about AVL trees, AVL trees keep everything so tidy, right? And eventually, keeping everything so tidy actually makes it easier just to add a new thing to the tree because you can find the right spot pretty fast. You don't hardly even see it until this point, though. At this point, the red-black tree is doing so much less work to stay in like a semi-messy or semi-tidy state that it's still faster to just like not do all that cleaning up. But at this level, the state of the tree is so imbalanced that adding a new thing is actually just as much work. So I'm sure it's going to be the opposite at the next time, or not. I had a hypothesis, and it broke. It's still the case that if you get randomized input, you know it's randomized, it's better to not do any of those rotations. That's why the BST is so fast. It's just inserting them, and it's not that imbalanced. AVL is still doing a bunch. Red-black is doing less work, but it's not being super penalized. Okay, so that never actually becomes. So if it's the case that red-black is, or the AVL's clean, tidy, super tidy state is helpful on insert, it's not captured in, like I skipped it because these things are each 10 times apart. Can you imagine what 100, 1,000, 10,000, 100,000, a million looks like on a number line? You with me? They're not linearly separated, so you can't, don't forget that when you're looking at this. If you draw a line between these things, then that actually means it's, does that mean it's logarithmic? Am I doing that backwards? Your input is increasing times 10. If it were linear, you would expect it to increase by 10. Okay. So these are the kind of questions I'd like you to explore in the report, like a lab report, is what behaviors do you see? And there are a lot of different comparisons to make. Another way is to say, okay, well, how does the dictionary compare to the BST? And you'll see that it always kills it. That linear time, it's just better. Now, maybe we're not seeing the whole picture, and maybe the space helps us see that. Oh, can I not scroll in this? Okay. If I zoom out, I can see it. Can you see that? The dictionary at this baseline inserted 7.2K, but the BST just was like half of that at 3.95K. So it's got twice as much memory, but it's crazy fast. Does that pattern still hold? I mean, the red-black is still using them. That's using a ton of memory there. So what's cool about this to me is this is the real world with all the messy details, some of which you can't even see. Like all this depends on the implementation of these things, some of which like, you can't see Microsoft's implementation of the dictionary. I don't know if that's open source or not. I didn't think it would be. Okay, so I'm going to share this code with you, and I'm saying the code that you're going to write is pretty minimal. And for this lab, this is to me like a lab in physics or chemistry. You're going to run a bunch of experiments and then report the results that you had and then analyze those results based on the theories that you've learned. And you can see how well the theory and the practice align. I would think that I expect there to be your data in tables in the report and meaningful charts that explain these patterns. You cannot put all the data on one chart or it's just madness. In a similar way, the scale is so different that if you put anything on a chart with a BST, with large input, then the BST is so, especially a BST in an ordered way, the BST is so slow that it just dominates and that's all you can see. So you're going to want to exclude the BST on some charts so that you can actually see how the other two or three compare. Does that make sense? So you got to use your brain to decide, oh wait, that doesn't actually show anything except I've got this big thing and then these three lines, they're all squished together at the bottom. Okay, I've talked for too much today. Questions, concerns? You feeling it? So absolutely, your big input here, your deliverable is a Google Doc with text explaining what you did and your results and an analysis of those results. And I'm happy to share with you like an outline or maybe an example of the kind of document I'm expecting. But this is the case that getting the data, running the code is like 10% of the project, maybe 20. So you can't even hardly begin to work on this until you have the data. If you wait to the last second to get the data, you're going to do terribly on the report. And the report's the main thing on this one. I'm going to send you the videos for red-black trees from Rob. It's just another way of enforcing balance. The rules may seem arbitrary, but if you just trust that there are rules that help move the tree in a balanced way, but they're not as hardcore as you can't be more than one difference in height. So we'll have a similar red-black tree video assignment for next time. Hopefully you can, definitely I would like you to make sure that you can get this code running on your computer for next time, by next time, and address any concerns technically there. And I would like to introduce another data structure that's based on a tree next time that I think is really simple that we may code up but it's going to be really light on coding and more of a, you want to have this tool in your tool belt and know what a heap is, because heaps are really commonly used. Thanks for hanging with me. I hope you guys have a good day. God bless.